Okay, welcome everyone to my continuation of what is algebraic graph theory. Today, I would like to talk about matroid embeddings. So kind of the correct notion for greedy algorithms. So every greedy algorithm comes from a matroid embedding, and every matroid embedding corresponds to a greedy algorithm. Problem is, matroid embeddings are a little bit annoying to define. So I'm actually not going to talk about them at all. And I'm actually talking about a slightly different notion, which was invented in the middle, so matroids first, and people thought about how can we kind of beef that up to get every greedy algorithm, and then people discovered the Greedoids. This is what I'm going to explain. In the very last slide, I will go to the newest notion, which are those matroid embeddings, but they're a little bit, it's not super difficult, so the definition will fit on the slide. Not terribly difficult, but it could be better. Let's just say it how it is. It could be better. So I decided to kind of push the statement a little bit behind, and we talk about Greedoids for most of the time. And just really keep in mind what we are looking for is the following statement. A greedy algorithm should be equivalent to a matroid. That's not quite true. So what do we need to do to fix that problem? That's what we are going to look at today. Okay, and let me remind you what this was. So we had this spanning forest algorithm. And this one, the one we discussed, actually goes back to Klushkal, and it's usually called the Klushkal algorithm. And it's kind of really nice. It's really just picks the smallest edge, okay? So picks the smallest edge, pick the smallest edge, pick the smallest edge, pick the smallest edge, always the smallest available edge. And you never pick something so that you get a cycle. So pick the next smallest edge, and so on and so on, right? So then you can pick this number 5 and whatever, and then eventually you get to the spanning tree, which is kind of a really, really exciting statement, because you just always do the naive thing. You just pick the smallest one and you get to the minimal spanning tree. And that's a kind of a standard example of a greedy algorithm. Very surprising if you see it for the first time, but maybe you're not surprised anymore by now, because this really comes from a matroid, right? So this one actually comes from a matroid, from a graphic matroid in this case. There's another way of doing it, which is kind of the rule way of doing it, and it's named after Prim, so it's called Prim's algorithm, and it works slightly different. It also gives you a spanning forest. So it's essentially you grow the tree from a chosen vertex. Okay, so in the other algorithm, I pick an edge, I pick an edge, I pick an edge, I pick an edge. I never pick any vertex. I just pick edges. So that's how it works, and that's why it's related to a matroid. And here I start with a vertex and grow from there. So I start with a vertex A, for example, or any vertex, and I pick the next accessible edge to A with the smallest weight. And I keep on going. I always pick the next smallest weight that is neighboring my new tree. And I'm growing a tree from A onward and so on. Right? So difference to Klushkal, to the previous algorithm, here I pick a vertex and then the next accessible edge. In Klushkal, the next accessible smallest edge. It's again a greedy algorithm. Always pick the smallest one. In Klushkal, we just pick edges. There's always the smallest one. And you can kind of convince yourself that this one cannot come from a greedy algorithm. Sorry, it is a greedy algorithm, but it cannot come from a matroid, simply because of this kind of bias that you pick a vertex at one point. Okay, so this one is not realized by a matroid. And that's a bit sad, because it's essentially the same algorithm as the other one, right? You always pick the smallest available edge, but there's some bias in it. You need to choose a vertex here. And people, of course, knew this example for a long time, and Klushkal versus Prim, and they essentially needed to, there was this idea to extend the notion of a matroid to include Prim's algorithm. And what you get, if you would think this through, is this notion of a Greedoid, okay? So we can just compare. And this is why I prefer the Greedoid over the matroid embedding, which I'll show you later in a second, because it essentially looks like a matroid. It's just slightly different. So a Greedoid is really a mild generalization of a matroid, and it essentially still includes greedy strategies. So every matroid is a Greedoid, but for example, there's Prim's Greedoid, which is not a matroid, that gives us Prim's algorithm. So included are now both Klushkal and Prim. So let's have a look at the definition. So matroid is this existence of linear sets, and here we for Greedoid, it's essentially the same. They're just called feasible sets. Forget it. So existence of feasible sets, and this one looks slightly different. The existence of existence of linear sets, linear independent sets, and the existence of feasible sets, which looks slightly different, but it's not super different. And the vector exchange property is also essentially the same. I just put them next to one another, but it's slightly different. And having something slightly different kind of makes the whole story work. That's why this definition here actually includes this definition. Otherwise, it looks exactly the same. You have a finite set, your ground set. You have this choice of feasible sets or linear independent sets, and you have some condition on those sets. And here you really see the following condition. If, well, it shouldn't be empty, but if this, by the way, implies that F is not empty. So if there is a set in it, and it's not empty, then you can take out an element and you're still in F, which is different from this one. Here we just say we have this condition instead, right? So no, not this one. This was too long. This condition instead. So if we have a subset, then the subset is also an I. And here we only say that we can take out an element and we are still in our feasible sets. So it looks very, 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 very similar. And that's why I usually like to say matroids are already good enough, because this is just a really tiny extension. But you can convince yourself that this one would include Prim's algorithm, actually. And that's essentially the statement. So the greedy algorithm works essentially for all Greedoids and all weightings. And the converse is, again, almost true. Yeah, so it's essentially what it should be. And there is a difference between the matroid and the Greedoid is that in the Greedoid, you have a slightly weaker notion of kind of subsets of independent sets. So here's an example, right? It's an independent system. And in a Greedoid, you could, for example, exclude two. That's absolutely possible. And that's somewhat the generalization. The point is, so people discovered them very, very quickly after matroids, because this question of having a perfect algorithm, having a perfect description of greedy algorithms is just very natural. But turns out that they're not quite do what you want. There are still greedy algorithms that do not come from a Greedoid. That's a bit of a problem. And some Greedoids actually do not return the optimal solution. So that's why I have this funny admissible weightings here, which I'm not going to explain. So it's a generalization, and it includes essentially all examples that you ever want, but it's not quite what it is. And the real correct notion that's kind of equivalent to greedy algorithms in the sense that the paper that defines it makes it precise is the notion of a matroid embedding, which I personally find much more difficult. So here for a Greedoid, essentially you just weaken the condition of what a linear independent, the set of linear independent sets is supposed to be, and that's essentially it. But for a matroid embedding, well, I just put the definition here. As you can see, it's certainly longer and more difficult. But anyway, so let's not have a look at it too much. You probably won't need it too much. Just keep in mind that there is a notion of a matroid embedding, which of course includes any matroid. Whatever you see above, that's what it is. And now all greedy strategies come up from a matroid embedding. And the way people really found this is to just write down, start with a greedy algorithm and see what kind of abstract axioms you need to generate it in a matroid fashion. Okay. So the story here is Greedoids kind of a natural generalization of matroids. They almost do the job. Matroids almost do the job anyway. And then, yeah, okay, you need to tweak the definition quite a bit to get the correct one, but at least the collection of all subsets here form a matroid. So yeah, so you generalize a matroid in a sense, in this sense, and you get what is called a matroid embedding, and that's a perfect description of the greedy algorithm. Anyway, that was about greedy algorithms. So greedy algorithms, I still want to sell the idea that they're essentially the same as matroids. It's not quite true. Hopefully that became clear. Fixing that is a bit of a pain in the neck. Hopefully that became clear on the previous slide, but people know how to do it. That's essentially what I'm trying to say. So we can somehow forget about the difficulties and just kind of say, I would like to do that anyway. The matroids and greedy algorithms are the same, which kind of is the whole point of matroids. Anyway, I hope you enjoyed this video, and I also hope to see you next time.